Alright, so very short class, just from 12:30 to 1 p.m. Because of my vaccination shot, and we're going to jump right in here. So today's section is 5.3 graphs of polynomial functions. And when you graph a polynomial function, you'll often get something that looks like this shape. These wiggles. We call these things the turning points. There's 3 turning points because it's going downhill. So if you were having stock, you'd be losing money. And then when you turn and you go uphill, you're gaining money. This is called a turning point. Here's another turning point. Here's another turning point. But what we're going to focus on first, before turning points, is x-intercepts. Where do you cross the x-axis? Here, 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 and over here. But some of them we call crossing, and some of them we call touching. So, if this one over here, on one side of this point, it's above the x-axis, and the other side it's below the x-axis, then we crossed over the x-axis. But look at this one. To the left of 2 on the x-axis, you're below the x-axis. And to the right of 2, you're also below the x-axis. So you just came up and nicked the x-axis and then went back down. That's called touching. While when it's passing from below to above or vice versa, it's called crossing the x-axis. Alright, so this, when we graph polynomial functions, we'll never get the graph right unless you really understand this part. Touching and crossing, and what causes you to touch and what causes you to cross. Alright, we'll get to that when we talk about multiplicity. So, on multiplicity, let's take a look at this function. This is a polynomial function. If I was to expand this out, it would look something like this. F of x equals, now to expand this out, you'd have to write x minus 3 twice. X minus 2, x minus 1, and you'd have to like FOIL these two out. Get that result, FOIL that with this. Get that result, multiply that with this. And then distribute the 2 to everything, every term. And what you would get is, if you took the x from each one of these, you see the leading term would be x to the 4th. And this 2 out front would be the coefficient of this. Now, there'd be other stuff after this, but you can kind of tell that this is a 4th degree polynomial with leading coefficient that's positive. All right. Now, we know the zeros. What causes x-intercepts is when the input causes the output to be 0. If you put 3 in as your input, it causes this to be 0. 0 times anything is 0, so the output is 0. Since the input that causes the output to be 0 are called zeros. Now, there's also other names. Zeros are also called x-intercepts. Of a function. And what we say is the multiplicity of 2 and 1, we can look at up here, these are multiplicity of 1. But this one, if you plug in 3, somehow that causes 2 zeros in there. So we call it multiplicity 2. It's the exponent on this term that caused the 0. So it's multiplicity 2, 1, and 1. And now we're going to look, create graphs of each of the following. And we're going to pay attention to whether they touch or cross the x-axis and the multiplicity of the 0. Alright, now these are the very simplest possible functions. This one is the same as y equals x minus 0 squared. And if you plug in 0, it causes this thing to be 0. So the 0 is 0. And so if we graph y equals x squared, the x-intercept occurs at 0. But notice we are touching, not crossing. Now, the reason why we don't cross is because this is an even exponent. Let me show you why the even-powered exponent causes this not to change to the below the x-axis. We stay above the x-axis. If you plug in negative numbers, like -2 and -1, what do you get? You get positive. Now, instead of writing them like this, though, let me write them like this. And we get 4 and we get 1. So notice we're always getting a positive result. Now, when you, even at -0.01, when you square it, negative times a negative is positive. Okay. But when you jump to the other side of the x-axis, and now you're at something like positive 0.01. What happens is it causes 2 changes in sign. Now, it caused 2 changes in sign. Which cancel each other. And you're back to positive. And so you're getting exactly the same result when you cross over something that had multiplicity that was even. By crossing over, you cause something that was negative to become positive. The thing in parentheses was negative, but that happened an even number of times. An even number of negatives multiplied together is back to being positive. So that's why it just touches. Now, this one, in contrast, if we graph y equals x cubed, you get this shape. Well, let me do it a little bit better. Something like this. The right-hand side of this looks kind of like the right-hand side of this, just a bit steeper. It's like a right part of the parabola. But the left part of the parabola went down below. Why does this one, now this one is what we call crosses the x-axis. crosses from below the x-axis to above the x-axis. Why does this one cross while this one went and touched? Because this was really x times x times x, x cubed. And when you jumped over from one side to the next, so let's say we were at negative 0.1 to positive 0.1. Negative 0.1, you had three negatives multiplied together. Three negatives gives you a negative. I think we would count and we'd move the decimal 3 places to the left, you'd get like this. Alright, so, but when you jumped over from being negative to being positive, from negative 0.1 to positive 0.1, this sign changes. But this one does too, and this one does too. An odd number of sign changes does change the sign. And that's why you jump to the other side. When the multiplicity is even, what we're going to see is one thing happens. When the multiplicity is odd, because remember this is really x minus 0 cubed, and so it's a term that's odd multiplicity, then we get this crossing happening. And quick sketches of these two now. If I had y equals x to the 4th, that looks like this. It's kind of like a parabola, but it just goes up a lot steeper. And once again, it touches for the x-intercept. And x to the 5th, that's going to look like this one, but even steeper. And here it once again crosses the x-axis right there. All right. So, how does the multiplicity affect the graph at the x-intercept? Well, the answer to that question is this theorem. For a polynomial function, if the multiplicity of a 0 is blank, then the graph, and I'm going to start you out on this. The multiplicity is odd, then the graph does what? If the multiplicity of a 0 is even, then the graph does what? So, go into your group chat and type in what you think the correct response is on each one of those. And let me give you a quick 30 seconds. And group 2, what do you have? If the multiplicity of a 0 is odd, then the graph...
We put, for the first one, we put crosses, and the other one touches.
That is correct. If the multiplicity is odd, then what happens is when you cross over and change from a negative input to a positive input, or something like that, then it causes an odd number of changes in sign, and that'll change the sign. But if it causes an even number of changes in sign, it'll stay the same sign, so it just winds up staying above the x-axis both places, or if it was below, it stays below. Okay, crosses and touches. All right, so the function that we started with was this one. And we made this multiplicity chart, the zeros and their multiplicity. Okay, now let's go back to that function. To graph this, we first do the following. So now we're going to do the zeros and the multiplicity, and we're going to put either a T or a C in the bottom row for whether it touches or crosses the x-axis at that x-intercept. So let me give you a minute to get ahead of me. Everybody fill in this chart themselves, and then I'll fill it in a minute. And also part A asks you to determine the end behavior. I'll do that too. Okay, 20 seconds more. Excuse me. All right, so the end behavior, we notice that this f of x, it would be x squared to the third to the fourth, is 2x to the fourth plus lots of other things. So the end behavior just comes from this. And what we say is the end behavior is we can draw a little picture of it, like this. Or we could describe it in words, we'd say both up. At the far left, you're going up. At the far right, you're going to go up. That's the end behavior of this graph. Now we're going to complete the x-intercepts table. The zeros, if it's factored, the zeros just jump out at you. 3 causes this function to be 0. 2 also does, and 1. The multiplicity of this one was 2, and these had exponents of 1, so their multiplicity of 1. And then if the multiplicity was even, we say it touches. If it's odd, it crosses. Like this. So now we have a fair amount of information about this function right here. To graph it, we would want to determine one more thing, which would be the y-intercept. Now the y-intercept, remember, to get the y-intercept, you make a little table and you set the opposite letter to be 0. X to be 0. Now if x is 0, you're going to get what? 2 times negative 3 squared times negative 2. So this is all f of 0 times negative 1. Just plugging in 0 for all this. Now this turns out to be 9. And then there's, because 2 negatives, negative 3 times negative 3. And then here's 2 other negatives that make it all positive. And then 9 times 4 is 36. So the y-intercept is 36. So we have the y-intercept, 3 x-intercepts, and we have the end behavior. With all that information, we can now sketch a graph. To sketch the graph, So I need to make my scales the right size. The x's only need to be as large as 3. The biggest x-intercept is 3. But the y's, if I just went up to 3, I mean in the same scale, I'd never get up to 36. Now it's perfectly legitimate to go in one direction by like 10s. You often have to do this. And the other one by 1s. And we make even these even bigger than those, and they're only 1s. We especially have to do this like if this was the year and this was, thousands of dollars, we'd have to go by 1s here and we'd have to go by thousands over here or millions over here. So it's often changed the scale. And now we're going to put the x-intercepts. They are, I'd put them as dots, except this thing won't let me do that. I'll put them with little x's. At 1, at 2, and at 3, we know we have x-intercepts. And the y-intercept we know is at 36. Right here. We also know the end behavior is both up. Now, let me show you how to do this wrong at first. The wrong way to do this would be go whipping through here, whipping through here, whipping through here. How do I know that that is wrong? Because the end behavior was both up, and I ended up with down on the far right. How in the hell did I end up with the wrong thing? Well, because I wasn't paying attention to the touches and the crosses. If I pay careful attention to the touches and the crosses, I won't have this thing that contradicts the end behavior show up. So let me undo that. Now, let's do it again, and we're going to put next to these things, these little tiny cross, cross, and touch. Now I'm going to make my graph through this, and I'm going to come this one, I'm going to cross it, so it means go to the other side of the x-axis. Now, I don't know how far to go down. Maybe I go way down, maybe I go a tiny bit down. It doesn't matter. The only thing that we really want to make sure that we're getting correct is that we're on the correct side of the x-axis. Come up here, we're going to cross again. We come here, and this one is touch. The only way you can do the touch nicely is you got to come below it a bit in front of it, and then level out at it, and then come back up like this. When you do the touching and the crossing correctly, you don't get this contradiction of being on the wrong side of the x-axis to match up with your end behavior. And they'll be confirming each other. Doing the touching and crossing correctly will confirm, oh yeah, I did the end behavior right, I did all of this. And when you have this kind of thing, you could also go to some program like Wolfram Alpha. Let me go to wolframalpha.com, something that will graph it for me. Y equals this. And then I hit enter, so I copied and I pasted it in here. When I enter it, it will show me what it thinks I meant, and that looks good enough. It has extra parentheses, but that doesn't hurt anything. and then it shows me the graph. And it touched way out here at 3. Both ends are going up, and it didn't go down very much, down to -1 and up less than 1. That part doesn't really matter so much. We know that our scale is going to be a bit off on these loops in between, but we want to be on the correct side of the x-axis each time when we do these. Alright, so I can go to graphing utility, something, or a graphing calculator and check my work when I'm done. Very important on here. Don't go plugging it into a computer or graphing calculator before you do all this work. You need the struggling part. That's how we learn. It's called, in learning theory, it's called desirable difficulties. And if you take away those desirable difficulties by, cheating and looking at the answer first, and then you never struggle with any of the problems, and then come test time, you struggle like crazy. All right, so the other thing I want to touch on really quickly is create a possible function from each graph. We learned last time the maximum number of x-intercepts, but it's not the same as the maximum number of x-intercepts is the same as the degree of the polynomial. This is a 4th degree polynomial, but we only had 1, 2, 3 x-intercepts. That's because one of the x-intercept had more multiplicity that was higher than 1. So it doesn't create a whole new point, but it does affect possibly how it touches or crosses. All right. Now, so it can have degree 4 and have up to 4 x-intercepts, but only up to 4. The maximum number of x-intercepts is 4 if it's a 4th degree. Now, if it's the number of turning points that we're looking at, the number of turning points is 1 less than that. So let's look at this one right here. I'm going to create a possible function from this. I'm going to say f of x equals, and x minus 3, -3 is a 0. That means x plus 3 had to have been one of the factors, because then when you plug in -3 into here, it causes the y to be 0. -1 is a 0, so x plus 1 must have been a factor, because plug in -1 and you get a 0. X minus 3 must have been a factor, and you're going to get this. Alright, now I could say here's a possible function for this, but notice this would be 3rd degree. If you FOILed this out all the way. Now 3rd degree has this kind of end behavior, because put a positive 100 into it, you're going to get a positive result way on the far right. And this end behavior is the opposite of that. So how do I adjust this to match that? I must have had an extra negative sign that switched the end behavior around. So here is a possible function for this one right over here. Now you could also adjust it more carefully than that, but I'm not going to get too concerned about that. Like for instance, if you plugged in 0, do you get a height of 2? And if you don't, you just put a constant out here that'll adjust the height right there. But I'll be more concerned about, do you get these intercepts correct? Do you get the multiplicity correct? And do you get a positive or negative correct out here? So the homework is 5.3. Remember also, this 3rd degree polynomial, 2 turning points. The maximum number of turning points is 1 less than the degree of the polynomial. So that is consistent with the picture. You have enough information now to get going with 5.3. I'll be generous with the spot check. So, if you get, a bit less than 75%, that's okay. But you should be able to get a fair amount of the homework done with going through, get as much as you can get done from what we learned today. So, we will stop at this point. Anybody have a quick question for me or anything? All right, I've got to run.